So we've come to something called the Aufbau Principle, and we're gonna explain this. I'm gonna explain it at first, like how you're gonna use it, and then there are some fundamental ideas that you need to understand about um, why it is. Okay, and we'll go to quantum mechanics and stuff for that. But the Aufbau Principle is pretty straightforward. It just means the building up or construction principle. It's how do you make an electron configuration. And so I sort of highlighted a little bit of how it looks, okay? Now, normally this is all written out in one string, but what I did is I broke it up and I made colors here so you could see the individual periods. So like 1s, S stands for the s orbital, of course, and so you can put 2 electrons in there. And then 2s is the 2s orbital. It could put 2 electrons in here. But when we say 2p, we're actually talking about 3 different orbitals. Remember, the p subshell, right, is made up of px, py, pz. And because of that, in each of these orbitals can take 2 electrons. Because of that, there's a total of 6 electrons that you could put into here. And then if you're looking at the next energy level, you're looking at 3s, 3p, the 4s, 3d, 4p, right? This is actually the first period. So let's go over to the periodic table real quick. First period, that's 1s, and then 1s1 and 1s2, right? There's 2 elements here, so those are the first 2 electrons. In the next row, that's 2s and 2p. There's 2 here and 6 here. That actually represents 2 right here, and 1, 2, 3, 4, 5, 6 over here. So there's 3s, right, and then 3p's. There's 6 over here. And then notice the next row down. That's this one, 4s, which would be 2 electrons. 3d, which is 10 electrons. Remember, the d orbitals, the subshell, is made up of 5 different d orbitals that got names dx, y, yz, xz, x squared, y squared, and z squared. That's 10 electrons. So when you're looking at those 10 electrons, it's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's 6. So this is 4s, 3d, and then 4p. Okay. So the general principle is on the periodic table, this represents n. These numbers. The periods are the principal quantum numbers of the highest energy level in the electron configuration. But these are all n minus 1. The other thing I wanted to do, and I sort of stopped and I made a little edit, so I hope this sort of mixes in well. But this represents S, this represents P, and these, the transition metals, they all represent d orbitals. Okay, and then these ones down here, and I'll like interject again when I go back to the main recording. These represent the f orbitals down here. Now you'll notice what happens when you get down here. We could do 5s, 4d, 5p, 6s, and then what happens is we shift down into the f orbitals. Now when you shift into the f orbitals, this is actually 4f. And this is 5f that's down here. So they show the lanthanide series and the actinide series broken out down below because these are representative of the 4f and the 5f levels. Now the real reason why the periodic table looks like this, now remember when we looked at Mendeleev's periodic table, these weren't in the middle, they were sort of interspersed, and that's because we didn't know about the atomic numbers and we didn't know that the transition elements were fundamentally somehow different. But the transition elements then became this transition between the very the alkali earth and the alkaline earth metals, and sort of the non-metals on this side. And also they are called the main group because remember when you looked at the periodic table, these were all the A's. And in the original periodic table, some of these were stuck in the middle. But once we figured out the atomic numbers, they got spread out so that they were in the middle of the periodic table. And that was for good reason because they represent a fundamentally different sort of structure of atom that's producing the chemistry there. Those are the d orbital elements. But then this is almost like after all of that, right, and getting it to be like this, in reality, these should be in here, and this whole periodic table should be split one more time. And the reason they don't do it is because it's a huge waste of space, like when you publish it, right? But there are people who will take this periodic table and cut it and stick these in here and then spread these out, okay? But these are the f orbitals. Now, I don't want you to remember necessarily everything about the Aufbau principle. I don't want you to memorize it. I'm teaching you so that you'll know where you're at in the electron configuration by looking at what period you're in, right, and where you are in the periodic table. But there is a fundamental question in here, and the fundamental question is, why don't the 3s electrons, right, and the 3p electrons immediately precede the 3ds? I mean, why is there a gap here that you have to step down, and so 4s and then you do 3d? In order to understand that, we have to take a closer look at some fundamental principles about the way electrons interact within atoms. So to start with, we're going to talk about something called Coulomb's law. And Coulomb's law, it's basically that law that you learned about opposites attract. So if you have an oppositely charged object, right? So let's say I have a -1 charge over here, and I have a +1 charge over here, that there will be an attractive force or force of attraction between these two objects, okay? So think about what that means in Coulomb's law equation. Now, this is all constants, and you don't really need to know what these things are. This is just call it K. But these are the charges. And they're charges of oppositely charged. They're the charges of two objects, preferably point charges or small spheres. Let's think about it this way. And r is the distance between their centers, okay? So that's the radius. And that's why I say it's point charge, so you don't have to think about how wide the thing is. But this is r. That's distance separating them. Now, if you have a positively charged object and a negatively charged object, so let's say E, right, is equal to then K times a -1 and a +1, and this is R. As R gets smaller, right, what happens? The energy, is actually a potential energy, gets more negative. So if you think about the way this equation looks on a graph, like this. If I have an object over here and an object over here, and let's say it starts off infinitely far away. And now, you really can't get infinitely far away, but let's just say you could, okay? Then r would be infinity, and then if you divide anything by infinity, what you get is 0. So I'm going to put 0 over here, and that's the energy of potential energy between the two objects, okay? That's a little bit too big for an axis thing. Okay, and then what happens is as you get closer, right, this number gets more negative. So it's going to go like this. Okay, and it heads downward. Sort of like a 1 over x, right? If you're familiar with the math of 1 over x, it sort of heads downward. And it'll keep going down, and this eventually, if this comes out to be 0, then this will go all the way down to negative infinity. We'll talk about why it doesn't do that a little bit, but yeah, so that's Coulomb's law. But now think about this as well. If I have two positively charged objects, right, what happens? Well, they start out infinitely far away. So this is, I put infinity on a graph. I always like doing that because, that's a really long axis. Then what happens is, let me do it in a different color. It's letting me do it now. Then what's going to happen is it'll have the same shape, but it'll head upwards, okay? And that's repulsive. So think about it like this: if you're higher in energy here than you were here, then you would rather be here. On the other hand, if you're lower in energy here, then essentially you'd want to get closer and closer and closer together, which is why we say, opposites attract. We say that for Coulomb's law, but we also say that for like people and their attractions. And the closer they get, the more attracted they are to each other. Okay. So positive particles, like positive charged particles, right? If I had a positive and a positive, or if I had a negative and a negative, that produces the same effect, right? It's only oppositely charged that will go down in energy and go to a lower, more stable energy, a lower energy. Okay, so next, a couple other things. If I change the charge of the object, so I said +1, -1, right? What if I had made this -1 and +2, right? Well, then it would be twice as big. And that curve, if I was drawing it over here, in tiger orange, I guess, would be dropping twice as fast. Well, it's not really twice as fast, but you get the idea. It'd be going down twice as fast. So the force of attraction would be stronger. If they were both doubled, then it would be 4 times stronger. If one of them's doubled, then it's just twice as strong. Okay? So there's 2 other effects we have to understand to sort of understand why the orbitals have different energies than we expect them to have. And they're called shielding and penetration. So let me sort of talk about shielding real quick. I'm going to draw a diagram on the next page. So let's say you have lithium, right? Lithium has 3 electrons. So N equals 3, right? So that means 3 electrons. And I think about how the electrons are arranged. So I have a 1s orbital. The nucleus is a 3+. But within that 1s orbital, I have 2 electrons. So I'm going to sort of highlight those. So that represents the 2 electrons. So the net effect is then that last electron, which is in the 2s orbital. Remember, the electron configuration for lithium would be 1s2 and 2s1. So I have 1 more electron, right? That 1 electron is out here somewhere. So I don't like drawing it as a dot. I should really draw it like I did for here, as I sort of drew it as a filled-in space. I should have really done that. Yeah, so that 1 electron, I should have drawn it as a cloud, right? But what I have is the 2 electrons in here as a cloud. Sorry, I couldn't get my pointer to work for a little bit. So what does this electron experience? Well, since this is a 2 negative charge, in the electron cloud, in the 1s electron cloud, then the net charge that this electron sees is it sees a +1 charge. Now, not every orbital has the same shielding ability. An s orbital has better shielding ability than any of the other orbital types. So, for example, and you can imagine why that is. If it's a p orbital looks like this, right? And so, if you're an electron, let's say this is 2p, one of the 2p orbitals, there's less efficient shielding in this region because there's no electrons in that plane. Now, if you superimpose all the p orbitals, then that spot's covered, but there's still little gaps in the shielding, and as a result, when you have an electron on the outside over here versus over here, the amount of shielding it sees is different. Here it has to look through the electron cloud over here. Here it has to look all the way through the electron cloud this way. So since it's not symmetrically distributed around the nucleus, that is, it has an angular node in it, then the shielding isn't as effective. And so for s orbitals, the shielding is most effective. For p orbitals, it's less effective. Every time you add an angular node, so a d orbital, right, would be even less effective than a p. So that briefly sort of describes what shielding is. Now, penetration is a little bit more difficult to describe, so I'm going to draw some images on the next page, and I'll show you the book image as well. Okay, so let's think about a 1s orbital, right? So here's my Just I'm going to draw a coordinate system like this, and I have a 1s orbital. Remember the 1s orbital, the radial distribution function. And I'm just going to do the one side. So I'm only going to draw on this side, but this looks the same on this side. It looks something like this. All right. So this would be a radial distribution function. There's radius, and there's this probability up here. Actual probability of finding electrons. So you'd expect the electron to be here, right? Now, let's take a look at a 2s orbital. If we look at the same function for a 2s orbital, remember, this is 1s. Oops. All those weird animations I forgot about. This is 1s. This is 2s. When you go from 1s to 2s, this has a radial node. And if you remember, in the images that we looked at, the 1s was a solid sphere, where the 2s was a sphere with a hollow spot in the middle of it. So this would be your 1s orbital, right? It's a solid sphere. This is the actual wave function, right? And then when I look at 2s, it looks like this. So this is a 2s, and you'll notice that part of it's blue, but on the inside I have that orange. Remember, that represents the change in sign. And in between those two, I have a radial node that is around the center in the very middle. There's a node where you find zero probability. If you remember why that is, the wave function for the 2s looks something like this. That's its radial distribution function. So when I'm looking at a 2p orbital, right? A 2s orbital, sorry. This is that region it's radially distributed going from the center outwards, where there's no electron probability, right? But here's the thing that's a little bit weird about penetration, right? Even though there's this node in here, if you superimpose the 1s and the 2s on top of each other, you get a graph. This is the book's version of the 1s versus the 2s. So here's 1s, right? Here's 2p, and here's 2s. And you notice what penetration does is it puts electron density for the 2s orbital inside the 2p orbital. In other words, using Coulomb's law, right, that electron is actually more strongly attracted to the nucleus in the 2s orbital than it is in the 2p orbital. What that does is it causes there to be a slight difference in energy in the orbitals. So if I'm looking at 1s here, and this is energy on this axis going up, then 2s would be here, and then the 2p is a little bit lower than that. So this is 2s, and this is 2p. It's lower because of the penetration factor, that it can sort of get to the middle of the nucleus and stay there. Because it's inside the it's actually because of the radial node, it has electron density inside the location of where you'd expect to find the 2p orbital. And this goes for every orbital on every energy level. So a 4s will be lower in energy than a 4p, which will be a little bit lower than a 4d, and it all has to do with that penetration, the ability to stick electrons on the inside of the other orbitals. So when it boils down to it, right, when you do this with all the orbitals at all the energy levels, right, so all the n equals 1 to principal quantum numbers, 1, 2, 3, 4, 5, 6, 7, for example, and you look at all the subshell types, so we're looking at S, P, and D, notice what happens when you stack the energies on one diagram. The 1s is lower than the 2s, which is lower than the 2p, which is lower than the 3s, which is lower than the 3p, but you notice what happens. The 3s and the 3p have been drawn down towards the nucleus because of penetration, right? and the ability of the orbital to get inside the other orbital. So here's the thing: the 4s, because of penetration, is below the 3d, and this is what gives us the actual Aufbau principle. From reading the energies of these diagrams, what you would have is you would have 1s, then 2s, and then 2p, and then 3s, and then 3p. Now right below, right, this is 4s, and then 3d, and I'm trying to draw them kind of like the energy, the way they are in terms of energy. 3d, and then 4p jumps up. It's a little bit higher. And then all of a sudden, right, you notice the 4p is even further below the 5s, and the 4s is above the 3p, right? So the gap here and here starts to grow a little bit. And all of a sudden you have 4d. 4p, you have 5s. I don't know if I drew that quite right, but I'll try to do 5s, and then 4d. And then you can imagine, right, the 4d, and then the 5p, and then the 4f's come in. And then if we go back to our periodic table, this is what you get, right? That's when at 6s, and all of a sudden you're into the 4f's down here. Okay, so that roughly explains the Aufbau principle and how it's derived, like the filling order, how it's derived from both the combination of Coulomb's law and attraction, right, to draw the electrons to the lowest energy level, but also because of shielding and penetration. So we basically have, in doing electron configurations, there's actually 3 rules. And we'll go over these 3 rules, but these are the 3 rules you need to know for doing the electron configurations. Now, I'm going to tell you up front, I don't expect you to remember the Aufbau principle, but I do expect you to be able to look at a periodic table and then read quickly what the electron configuration of an atom would be. And we'll save the description of this for the next video segment.